Okay, so there are some parallels with the previous talk, but hopefully you'll get something new out of this. So today I'm going to talk to you about large language models for humans. Before we get going, I better introduce myself. My name's Andy. I have a swanky job title called a principal platform engineer, working with something called Kubernetes, and I previously worked with data systems alongside data scientists, but I'm not talking about that today. That's my day job. I'm not talking about my day job today. Instead, I'm going to talk to you about what I've learned working with AI in open source projects, because that's where most of my knowledge has come from. I do, however, have a professional qualification in data science. Thank you, mother. It's not that impressive. And my main learnings from doing data science is it's 5% actually getting meaning out of your data and getting some results, and it's 90% cleaning and munging the data. One of my colleagues said, my day job is mostly like being handed a box of metal coat hangers and being asked to sort them out. That's kind of the thing data scientists do. And the other 5% is the moaning about 90% of the job being sorting out the data for that 5% and getting there. And fun fact, I wrote my first chatbot at 14, which was some time ago. Would you like to see it? Here it is. Yeah. I say I wrote it, I copied it from a book. It wasn't even my book, it was a library book. If anybody wants to take a look, I do have the book with me, and I do have it running on a laptop down there that's sadly gone to sleep. But if you want to come and play with the chatbot, grab me later. And following that was a glittering career in IT, so a good start. So the challenge I have today is to tell you all about large language models, but without using code, which is a shame because I like code, without using maths, and there is a lot of maths, but I'm not going to show that, but without using jargon. Now, that's a little bit tricky because, as we've seen, there is quite a lot of jargon. Fortunately, it's mostly the same jargon that Rachel Lee covered in her talk before, so hopefully you'll know about that. So in the spirit of the bingo thing we've got coming up, we have a little bit of a precursor. I've already ring-fenced the jargon I'm going to use here. So if you want to play along, get the card up, and if you hear all these words, shout out house in probably about 20 minutes, and you can win a great prize, which I forgot to bring with me. So, as a replacement, I have this bag of wine gums from Aldi. They are vegan friendly and they're very nice. So you can win these. It's the best I could do at short notice, sorry. Okay, so let's talk about large language models. Now, large language models are the foundation of all the AI solutions which we use and we build solutions on top of. So ultimately, when you're using something like ChatGPT or Claude and you fill out your question and you hit the send button, that goes to some servers in a data center somewhere, and ultimately that will interact with a large language model, generate a response, and that will be returned to you. And it's amazing, isn't it? It's absolutely amazing what these models do. They seem human-like, they seem to be able to reason, they know like everything, and they're amazing. And they sit kind of at the intersection, in my opinion, we can have a discussion about this if you don't agree with this, in the AI landscape, kind of straddling between machine learning and natural language processing. That's where I think they sit. You may have other opinions on that. But there is a whole field of other AI stuff that we don't really talk about because we all talk about AI and about chat. And if you've been working as a data science for the last kind of 10 years, you're probably a bit miffed at the minute that everybody thinks your job's to do with ChatGPT. And Lisa Becker has a talk later today at 2:30 about LLM washing. I'm definitely going to be there because there's a load of other stuff in the AI world that isn't just large language models. But I'm going to talk about them today. So, in the evolution of large language models, and we've seen a little bit of this already, is we go from the theoretical, from like the Turing test from the 1950s, questioning whether a machine can actually learn. And that's evolved to kind of like more rule-based and code-based stuff. So the chatbot I made when I was 14 was based on something called analyse, and that was from the 60s. And basically that took your input, chopped it up into words and recognized nouns and adjectives and things like that. But we kind of realized that storing information about the language in a statistical model was much easier to work with than it is to kind of analyze the language on the fly. And that's evolved itself into neural networks, which you've already seen, and I'll talk a little bit more about those, and the transformers that utilize those neural networks underneath. Now, neural networks sound kind of scary because it sounds like we're making a computer brain. And as we've seen Terminator, we know only bad things can happen if we do that. This is a brain cell. So this is what we're trying to emulate. I drew this myself, by the way. It's one of my brain cells. It's technically a self-portrait. And it has these things called dendrites, which take in signals from my other brain cells. I've got a nucleus which will make a snap decision, usually a bad decision, and will output its responses down these things called axon terminals. And all these are connected together with the other 86 billion brain cells in my head. Well, I used to have 86 billion. I'm not sure how many I've got left now, but most people have 86 billion in there. And that's how I think and I do stuff, and it's the same for you. So if we're talking about building a computer brain, we're taking inspiration from this, but we're working with something much, much simpler. So we work with these things called neurons, which are the little circles. They're the decision makers. But in terms of computer science, these are like really basic bits of coding logic. They're not like massive programs. They're tiny decision-making things. And we have these connections between these layers of neurons. And these are called weights, and we're also going to call them parameters, so I'll probably use that phrase interchangeably. And they sit on these connections between the neurons. And this allows the neurons to make decisions and come out with an answer. Let's have an example. So I've got a neural network here. I've filled it full of random numbers, and I'm going to train it on recognizing a picture of a dog. Okay? Now, unfortunately, computers can't see dogs or anything at all. Certainly neural networks can't. So we have to change that into a numeric representation. So we've got a numeric representation of a dog. So we put this through the network, and based on the numbers going in, the weights between the neurons and what the neurons decide, we're going to get a classification at the end of it, or dog or not dog. Let's see what happens. Goes through the network, not dog. It is a dog. Right. So then we have to do this thing called loss calculation and backpropagation, which you already heard about today, and I'm not going to cover that, but basically some of the weights in the network get updated to correct that error. So there they go. Some new numbers, and then we put our inputs through again for our dog, and we get the word dog. Excellent, we've got it to recognize a single dog. Let's try with a different dog, different numeric representation. Put that through the network. Not dog, stupid network. Right, let's get it to fix itself. We'll do the loss calculation, backpropagation thing, and it will adjust some of the weights, different weights this time, and we put our picture through, and it says dog, hurrah. Okay, let's try and catch it out. This might just say yes to everything, so let's put a different kind of dog through. What does it think of that? It's a not dog. Excellent. Well done, neural network. And let's put another picture of a dog through. Different numeric representation. It recognizes a dog. Excellent. It recognizes 3 whole dog pictures. Let's put it in production. It's probably ready. Let's not do that. So we probably should train it on a couple of the million dog pictures just to make sure that it does recognize what dogs are or not. And we can do the same principle with text, although the network would be much more complicated than this, as we've already heard about. So if I take a bunch of phrases and the next word, and I put several million examples through a neural network, and it does that backpropagation, loss calculation, fixie thing, we should get to a stage where I can put the words once upon a through the network, and it should say time. Clever neural network. In practice, things are a little bit more complicated than that, as we'll see. But the important thing I want you to take away from this is it's not the neuron bits and it's not the inputs that are important, it's those weights on all those connections between the neurons, which is where it's storing its learning. This is its knowledge. And we're going to see a lot of lists of numbers today in this talk. Not the maths, but you're still going to see the numbers. And we're going to call these weights, or we're going to call these parameters that are stored in models. Okay, now I was going to ask, what does this mean? But you all know now, don't you? So, okay, so as a recap, in case anybody missed it, the GPT in ChatGPT stands for Generative Pre-trained Transformer. The generative bit is it will make sequences of words. The pre-trained bit is we've taught it all about language and how to do a thing. And the transformer is the structure of the neural networks and the code and the LLM underneath that makes all that happen. Let me elaborate a little bit on that vague statement. So this is our transformer. We take words in, we get a word out. There are neural networks between the two. We call these blocks of neural networks, and they have names. We've got something called the embedding block, something called the attention and MLP block, and then we've also got the output block, and that will give us our next word. Let's see how that works. During this training process that we're going to do, though, this set of neural networks will generate a lot of these weights and parameters in all sorts of different categories. And we take these and we store these in the file, which is the LLM. So the LLM is basically the data and the definition of what's in there. And the transformer is the thing that uses that data to generate and train that data. So the training process, and again, this is hopefully a bit of a recap on the following talk, from the previous talk, sorry. We have several different training steps we go through. We start with the generative pre-train step, which is kind of the unsupervised bit, where we give it just loads of text. About an internet worth is probably what we need. And we put that through the training process. It does all that back propagation loss calculation and fixes all the weights. And at the end of it, we have what we call a base LLM, which understands English in this case. So I'll do questions at the end, my friend, if that's all right. I said house. I have not said one of the words on there. Oh, okay. I'm not sure how to police this now. Okay. Does anybody else think I've used all the jargon? I know there's one word I haven't said. Oh, maybe one of the rows, but I don't think that's how bingo works. At least no. Okay, this has gone a little off track now. I tell you what, your table can have the wine gums for interacting. Thank you very much. You can just have them. Thank you. Where was I? I was training an LLM. Yes, I got a load of text has gone through this process. It's got a base LLM. It's English, but it's not very useful. If we were to throw a question at this LLM with a transformer, it wouldn't answer it. It'd just keep elaborating on the question. And it probably wouldn't stop either, because it doesn't know how to do that. So the next thing we need to do is we teach it how to do a thing, in our case, answering questions. So we give it loads of examples of handcrafted questions and answers. And we put those through the model again and again, and it adjusts the weights and it learns how to answer questions and, more importantly, when to shut up. So we have an instructional LLM at that point. But this LLM has a few blips in it because it was trained on the internet, and the internet's full of bad things and inaccuracies. So what we need to do is evaluate what the model's spitting out and correct it. So this is the RLHF section, the reinforcement learning with human feedback section. So this is basically where we mark its output and tell it whether it's any good and tell it to go away and fix it. At the end of that process, we've got a chat LLM, which is good news because we can then use that out in the real world and use it to answer questions. Simple, innit? Right. These are a lot bigger, though, than the models which I showed in the little example. We had probably had like a couple of 100 parameters in my very simple example. The commercial models and open source models are much, 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 much bigger. We are talking billions, if not trillions of parameters. And the training process these go through is very time consuming, which is why you don't get one every month. They are released with kind of like quite considerable time gaps between them, because not only does it take time, it takes money. This is expensive to train. They take a lot of power, they take a lot of energy, and they can damage the environment. I will not talk about that. I'm sure there's a talk about that later. To give an example of the kind of numbers that are in these parameters, we have these embedding numbers, which represent the semantic and syntactical meaning of words. In ChatGPT 3, which we'll use as kind of like a reference model for this, there are over 12,000 numbers, 12,288 to be precise, for every single word in our vocabulary that we've got. So that's a lot of numbers. And each of the numbers in there mean a thing. So like the first number in the sequence could be something around sentiment. The next one could be something around like culture or tense or any of the other kind of like attributable things we can classify words as. And I'm vague about what they are. They could be, they might be, because we don't know. The model worked that out during training. We can do a load of analysis, which will be time consuming to work out what's actually going on, but these numbers are created by the model. It did that because it's cleverer than us. Okay. Now, how do we know that this has got semantic meaning? How can we actually see that? Well, if we can find a way to squidge down these 12,000, let's call them dimensions, or these attributes of each word into two and still keep the meaning, we'd be able to plot them on the graph. Unfortunately, we can do that. So these gendered words I have here, and the gendered words work really well for this, but I'm not trying to make any comments on gender here, but you can see there's a relationship between these gendered words. The distance and direction between mother and father is not dissimilar to the distance and direction between woman and man. But because words don't just mean one thing in English language. We have overloaded terms. King and queen do not mean gendered monarch. There are many other uses of that word, and therefore they don't follow that relationship which we're seeing for the other words. But there's semantic meaning in there, and we'll see how that is adjusted as we would use these in a model. As goes the parameters that comes out of our training process, there are a lot of them. As I say, there's about 617 million embedding parameters in there, but there's a lot more. Let's look at this 175 billion split up. There's a huge chunk of this that is related to what's called up and down projection. There's some which is related to key, query, and value, and the embeddings bit is just a slither of that. So although that's got a lot of meaning in it, there are plenty of other parameters that are equally as valid. So let's run through an example of our transformer running and using these parameters to predict the next word. Let's see how it actually works under the hood. So here is our transformer. We are starting with a list of words. We're going to put that through the embedding layer. That's going to generate us these 12,000 numbers per word. And then we're going to do something called attention and MLP. And then off the back of the numbers we calculate during that section, we are going to generate our next word. So the phrase we are going to use today is something that needs completing. We're going to do the sequence generation. So the phrase I've got is, I like to listen to music on my radio, commute. What could it be? Let's let the model find out. That's what it's here for. So the first thing we do, as I've said, is we put this through the embedding layer and we pull back those 12,000 numbers per word. You'll notice the word to is in our sequence twice and it has the same values because it's the same word. Okay. Then what we do is we store those embedding numbers in memory. We don't touch the model file. That's like read-only. We leave that because we're going to use it for other stuff. So we store these embeddings in memory and we're going to manipulate those as we go through this entire process, and that's going to allow us to predict the next word. Let's see how that happens. So that's using the embedding parameters. If we plot those out, we can kind of see there's already some sort of meaning there. You can see, like listen music is already separated from the other words, and that's the semantic encoding that's in those words, like we saw with the gendered words. There's meaning and there's context in those words. So, speaking of context, this example on the screen here, the word it means something completely different by changing one word in the sentence. So this idea of context is super important. And what it means is we need to start treating this phrase, or this sentence, a collection of words, as more of a phrase. It has, the order has meaning, and it's important, the order and the relationship between the words. So that's what we're going to try and do in what we call the attention block. So back to our example, we've got this phrase. We're going to try and work out where these relationships are and what words attribute meaning to other words. So we have this whole bunch of parameters called keys, queries, and values. Now, I'm not going to deep dive into this, even though this is going to be quite deep. But basically, these numbers here per word represent different values and attributes which we can use to calculate context. So the query is, let's think of it like if it was a dating profile, for example. You might have your query as being who you're looking for. So you might be looking for companionship, an outdoorsy person. The key are what you offer. So you may be, I don't know, good sense of humor. You might also like doing outdoorsy things as well. And then there's the values, which we probably don't put on the dating site because these are the real things that you offer. These are your kind of like personality traits. So you might be caring and loving. You might have an unhealthy obsession with Ed Sheeran. Or you might have previous relationship statuses that you could only describe as complicated. We probably wouldn't put that on a dating site, but that's encoded into the values there. So what we do is we look at the query for each word, and we compare that against the key for each word, and based on the maths, we work out where there's a connection between them, this context, and off the back of that, we generate some numbers which represent that contextual meaning, and we update our embedding numbers with that information. So we combine all that together with the value, so we pick out the value as well, and we pull that into our embeddings. So effectively, we've updated where things sit in that space based upon the relationships between the words, okay? That's what that's doing. But we want to enhance that a little bit more, and this is where my favorite bit of the talk comes in, where we introduce the multi-layer perceptron. When you go home tonight, you can tell your friends and family and impress them that you know what a multi-layer perceptron is. They will be definitely impressed. And what it does is it basically uses these two huge chunks of data, the up and down projections, which are like the yellow and the orange section, to add extra information in. So the up projection data holds loads of other stuff about contextual meaning of words, which we haven't got in the embeddings. So we kind of match and pull that information through into the meaning of our words, and then we do some sort of filtering with something called an activation function, don't worry about that. But then we use the down projection data to kind of like squidge it all back into the embedding numbers at the bottom. So what we end up with after this fairly complicated step of finding contextual meaning and enhancing that contextual meaning and enhancing the words further is we end up with a new set of numbers, and things are in a slightly different position on the grid, okay? They've moved to represent that information. So what we do is we do it a few times. We do it 96 times. So as we go through this, you'll see the numbers jump around and move as we go through the various layers. I'm not doing all 96 because we'll be here a while, but I've got a snippet of them here. And you can see this process is pulling together the words, and it shows that contextual relationship between the words. So you can see at the bottom here, we've now got like listen to music. That's the phrase. We've got on my at the top. It's understood that contextual meaning and moved the revised meaning of each of the words into the right place for this phrase. And then what we do is we forget about all of that, and we just pick on the last numbers for the word my. Because my is the current last word in our sequence, we want to find the next one. But that's kind of being pushed into the right place contextually and semantically by all the other words as we calculated them. So it's not been a waste of time. And it really helps with the training process as well when you go back the other way, but that's by the way. So we've got the word my, and what we do is we take those embedding numbers for the word my, these updated ones, being through that process, and we use the unembedding data, and we combine that together to calculate a score for every word in our vocabulary as to how likely the next word is. So these are the top 15. We've got some numbers there, calculations, and we can convert those to a percentage, to a probability. And you can see the most likely word in our data, in our training data, is the word phone. Now, up to this point, everything has been deterministic, in the sense that if we stop this and start again, we'd still end up with 17.92% for the word phone. But we don't want that with large language models. We're generating chat. We want things to look human. We want variety. We want variability in there. So we use probability to choose the next word, which doesn't guarantee us to pick the most popular one. And this is where this system now becomes probabilistic. It's no longer deterministic. It's deterministic. And this is great if we're doing some sort of creative process and we want variance in our output. And that's why one of the attributes which we see when we see the output from our chat systems is we think they're human because they have this variety and answer things different each time. So, quick recap. We put a sequence of words in. We converted each one of those to 12,000 different numbers and in the embeddings. We then took those embedding values and we went through a contextual match and some additional attribution in the attention and multi-layer perceptron block. And off the back of that, we took the final values for the last word in our sequence, the word my, and we calculated the probability of each of the words in our language model as to what comes next. And we come out with the word phone. All that for that. And then we do it again. So we put the word phone onto our sentence and we put the new sentence through. And we go again and again and again and again and again until we hit something called the end of sequence token, which basically tells the transformer to stop. And that's how we generate text in a large language model. So, bearing all that in mind, if we wind back to the beginning and we were saying these chat models seem to know everything, they're human-like, they seem to be able to reason. If we go way back to the 1950s to the Turing test, and the paper that kind of sparked all that off. No, there's another one yet, sorry, but the prize is already gone. Sorry, you'll have to share. You can have one each, everybody. It might not be enough to go around. So, yeah, we go back to the Turing test, and we think about what's actually happening with these models. Is this a machine thinking, or is it just doing very clever, glorified predictive text? based on what it was trained on. And the reason we might think the output from this is human-like is because of that variability, because of that variety. And that's great until it's not, until it starts hallucinating and making stuff up and telling you the wrong things and mansplaining to you. It's not right good at that point. And there are, ooh, is that me or you? I don't know what happened then. Anyway, but there's like the example kicking around the web at the minute about my screen going off and on. That's not good, is it? Is that me or is that you? It's me. Hang on. I can go to the other HDMI output on my Mac. Just one moment. Talk amongst yourselves a minute. So, who here is a fan of linear algebra? Do we have any in? Yeah. About 4 or 5. Excellent stuff. Okay, we're back. Thanks for that interesting segue. Right, so meanwhile, back at this. So this kind of phrase kicking around the internet, how many R's in strawberry? I'm sure you've seen it. And ChatGPT says 2 a lot of the time. And of course, that's completely discredited this whole industry because this is stupid. It doesn't know what it's on about. It doesn't even know that. But now you know what you know about how this works underneath. I've calculated, for not ChatGPT, for the model I've been working with, the probabilities of what the next word is in this sequence. And you can see less than half the time, we're going to get the word 3, or the number 3. Sometimes we're going to get 2, 1, could get anything. So bearing that in mind, I think we have to be wary that LLMs and chat aren't quite a solution yet. They're more of a tool we can use. So in order to get the right kind of output out of these tools, we need to start thinking about doing things a bit differently. So first thing we can do is write better questions. And Xian's on the talking in about 4.5 minutes, so I better get a move on, about prompt engineering. So basically writing a better query. Give your model a chance to create the right answer. Stop being vague. Create a better prompt. The other thing we can do is maybe change our model. So take multiple outputs, merge them together. I mean, I do that anyway. Whenever I want ChatGPT to tell me something, I'll run the query a few times and create a greatest hit of its output. You probably do that already, but it's called ensembling. The other thing you could do is get it to put out a single word answer and then just vote or look for the most common response. You collectively get it to poll the answer. And there's nothing that says you can't take your response and put it back in the model or even a different model and ask it if it's right. You can do that. It'll cost you tokens, but you can do that. Another thing we can do is we can do something called retrieval augmented. Yes, well done. That was the point. You'll have to share. Sorry. Basically, we can crowbar our own data into the responses we generate, and there's a session by Walter later that's going to go through that, and I'm going to listen because it's not as simple as it sounds, particularly with tables of data. But check that out. The other thing we can do is use a better model, use a different model, use a bigger model. There are loads of different providers now. You don't have to just use ChatGPT, and if you do, you could perhaps try a different model. You could use models which maybe are fine-tuned on domain-specific information. You could use the models which are a mixture of experts, which have kind of like multiple personas encoded into them. There are better and faster transformer architectures which will give you better results. Or you could just run a bigger model. You could go for one with more parameters. Generally, you'll get better results out. Or you could run your own. I use a tool called Anything LLM and Olama. Others are available. These are open source. I've got links coming up. I've got a lot of links for you. But really, just to summarize, so these systems are doing next token prediction. They're picking the next word. That's all they're doing underneath. And we're building these fantastic, amazing solutions on top of those, which are effectively revolutionizing the world, as Nigel was saying earlier. But we still have to remember that box of metal coat hangers that my data science friends work with on a daily basis. Getting the data right, getting good data into the models and into the training process is so super important to make sure that when you are querying the models, the responses that are coming back are based on good, clean, and correct data and not just a load of internet. Okay. The output is probabilistic, it's not deterministic, and therefore we have to consider this as a tool and not as a solution and work alongside it to get the outputs that we want for our solutions. Here's a very big list of links to the QR code. So if you scan that QR code, you'll get this slide deck, and obviously the links are in there. If you don't get it, because I'm going to have to flick forward in a second, come and see me afterwards. I'm more than happy to share all this stuff with you. And speaking of which, I am here for the next 2 days. Come and talk to me about this stuff. I have the chatbot running I wrote when I was 14, running down here on an emulator. Come and play with it and laugh at it. I won't be offended. That's okay. If you want to have a look at the book, you can, but as you'll see, there's links in here to download your own copy because the publisher made them available. And yeah, come and talk to me about this stuff. I'm super interested to know what your thoughts are, whether you agree with it, whether you think I've got anything wrong, whether you want more detail on this stuff. And have a great conference, and I will see you around during the breaks. Thank you very much.